Good morning, all. So today we are in the tutorial session of one of our NPTEL courses, Design of Photovoltaic Systems, that we have taken, and it is given by Professor L. Omanan from DESE IASE. So we'll be looking at few of the assignment questions, reference assignment questions that will provide you an insight into what kind of questions will come for your weekly assignments. So we'll go through few of those, which will give you an idea of how to approach each questions and what all to look into each of those questions. So one of the first questions is, what can be inferred about the values of the series resistance Rs and the shunt resistance RSH in a PV cell having a very low fill factor value? So here there are three parameters that we have to look into. One is the series resistance, shunt resistance, and fill factor. I hope all of you know what each of those terms means, since you have all gone through the first week's video lectures. We'll have a quick brush through of each of those parameters, and then let's see how to approach the questions. So the series resistances and the shunt resistance can be seen from the model of the PV cell. We'll just quickly draw the model of the PV cell. So we all know that the model of a PV cell has a photocurrent source IP, which goes through the diode model ID, and then it passes through a non-ideal shunt resistance, which is our first parameter of interest, and then it goes through a series resistance, which is Rs, which is the second parameter of interest, and then it goes to the load. So as you can see, ideally, so if we were to draw the IV characteristics of this particular PV cell, let's imagine if, okay, with our shunt and our series in place, we know that our ideal, the non-ideal IV characteristics would look something like this, where this is our VOC, open circuit voltage, and this is our current ISC, short circuit current ISC. So this is how our IV characteristics should look like if our PV model looks like this. So the question is, what if RSH and R shunt and R series were not in place? So if let's say R shunt was ideally infinite, or it is an open circuit voltage, and if R series was ideally zero, then we would not see a slope which corresponds to these areas, and ideally the open circuit voltage should, I mean, the short circuit current should be an ideal current source throughout that particular point, and your open circuit voltage should be an ideal voltage source throughout the area of interest. So the blue line basically indicates a condition where your R shunt is infinity, sorry, R shunt is infinity and R series is zero. So that is the most ideal form of PV source, which is practically impossible. And if there is a small amount of R shunt and a small amount of R series, your IV characteristic should ideally look like the red curve. But what if your R shunt is too low and R series is too high? So as and when your R shunt and R series goes on increasing, or in the sense R shunt reduces and R series goes on increasing, you can see that your PV curve starts shifting towards the lower side. That means the non-ideality starts stepping in more, and your IV curve becomes more and more non-ideal. So as and when the ascent, so if you see, if you go down this curve, go down this green curve, what you can imply is that your R shunt is basically reducing in nature, and your R series is basically increasing in nature. So, what our question asks us is, what can be inferred if the values of R series and R shunt resistances have, what can be inferred about these two parameters if you have a very low fill factor? So we know that, so ideally the fill factor of the ideal fill factor of this particular PV model is given by the blue curve, which is nothing but 1. We know we know this because the value of the fill factor, or the equation of the fill factor FF, is nothing but VMP IMP by VOC ISC. right? So for the blue curve, if you see your VMP and IMP is nothing but your VOC into ISC. So your ideal fill factor of the PV cell has to be 1. All other fill factors of which it includes the non-idealities has to be less than 1. So if you see the green curves, you can see for the last green curve, which is ideally a straight line joining from ISC to VSC, you can see that your VMP and IMP would somewhere correspond to that particular point, and your fill factor is nothing but basically the area under this particular curve uh, divided by VOC into ISC. So if you see the fill factor is very low, that means you have a very high non-ideality in your PV cell model, and thus what you can infer is that your R shunt is very less and your R series is very high. So as and more your R shunt goes down and R series goes up, your fill factor is going to reduce. So if you have a very low fill factor, what you can infer is that your shunt resistance is too less and your series resistance is too high. So that is what the first question is all about. So let's move to the second question. So the second question is, as the intensity of light incident on a PV cell increases, IV characteristics of the cell moves which direction? So let's draw an ideal, non-ideal IV characteristic of our PV model. So let's see what happens. So this is your I, this is your V, and this is how. So this is how an ideal. This is how an ideal, non-ideal IV curve looks like. So this is your ISC. This is your VOC. Okay, so we know that ISC, the short circuit current, is basically a function of photocurrent IP. So where do you get your photocurrent IP from? IP is nothing but the current source IP that you get from your PV source model. So this is so the IP corresponds to the photocurrent IP that you get from your PV source model, and we know that the short circuit current is a directly relational function of the photocurrent IP. So as and when the intensity of the light on the solar cell increases, you get more energy for the cell, for the electrons in the solar cell to jump from the valence band to the conductance band, and the short circuit current increases, and thus short circuit current also increases disproportionately. So you can see that ISC is directly proportional to IP. So as and when the incident solar radiation increases, ISE. So if your solar insolation increases, your ISC is going to increase in a manner proportionally. Okay. As far as the open circuit voltage is concerned, so these two, so the short circuit current and the open circuit voltage are the two parameters which determine how your IV curve is going to shift. So we have already seen how the short circuit current moves. We'll see what happens to the open circuit voltage. So as far as the open circuit voltage is concerned, and we know we have derived the relation in one of those video lectures, we know that VOC is directly proportional to a function of ln IP, where IP is again your photocurrent and ln is a logarithmic function. So as and when the solar insolation increases, so when the solar insolation increases, we know that our IP increases. If your IP increases, based upon this equation, your VOC should increase, but it should increase logarithmically. So we have seen that your short circuit current increases proportionally and your open circuit voltage increases logarithmically. So what happens is, so let's say this blue curve was under an insulation of, let's say, 800 watt per meter square. Let's draw a curve which is under an insulation of 1000 watt per meter square. So the green curve basically would correspond to an insulation of 1000 watt per meter square. And you can see that since the insulation is increased, what you can see that your ISC has to increase proportionally. So let's say your ISC has reached a point this way for the green curve, but the increase in the VOC would definitely be less than as compared to ISC, because VOC would increase logarithmically as compared to ISC. So let's say we have a logarithmic increase in the VOC as indicated by this curve. So what you can see that the new curve So new curve would look something like this. So what happens is if the insulation increases, what you have seen is that the green curve would shift upwards as compared to the blue curve. So if there is an increase in insulation, the IV characteristic would shift upwards as compared to the previous IV curve. Okay, so that's how the second question has to be dealt with. Let's move on to a third question. So the third question is which of the following statements regarding the open circuit voltage and the short circuit current of a PV panel will be correct when there is a change in insulation occurs? So we have actually it's pretty much a similar question in that sense. So we have already seen that with respect to the insulation, with respect to insulation, our short circuit current ISC is directly proportional to the photocurrent. However, VOC is directly proportional to the logarithmic of the photocurrent, where photocurrent is directly a function of insulation. Okay, so based upon these relations, we can see that as there is a change in, so we can see. So the options are the change in VOC will be more than change in IAC, change in IAC will be more than change in VOC, both VOC and IAC change at the same rate, both VOC and IAC remain unchanged. So we are definitely sure that there is definitely a change in both short circuit current and open circuit voltage when there is a change in insulation. So we can rule out the last option. So, and we have also derived the relation between how the change occurs for each of those parameters, and we know that we definitely know that the change in VOC ISC is definitely more than that for the change in VOC because of the proportionality. So one is directly proportional and the other is proportional in a logarithmic way. So we can, if we go back to the options, so this is not the wrong option because it doesn't change the same rate. So the only option left is ISC has a more change rather than open circuit voltage. So change in VOC is more than the open circuit voltage. So that is definitely the first option. Sorry. So change in ISC is definitely more than the change in VOC. So that is how the third question has to be dealt with. So now I pass on the presentation to the next TA, Anshul. She'll continue with the rest of the questions.
Hi guys. So far you were hearing from Ashwin. So myself and Ashwin together will be the TAs for this course. So let's start with the fourth question. So the question says the short circuit current and the open circuit voltage of a PV cell varies dash and dash respectively with insulation. So just in the previous question, Ashwin mentioned that insulation is proportional to the photocurrent. So the photocurrent parameter in our diode in our PV cell model tells us about the insulation that is falling on the PV cell. So and also we have seen that short circuit current is proportional to the photocurrent. Also, open circuit voltage is proportional to the logarithmic of photocurrent. So the same thing is being asked here. The short circuit current varies logarithmically, varies linearly, and open circuit voltage varies logarithmically. So this will be the answer to this question. So let us move on to the next question. As temperature increases, the efficiency of the PV cell, what happens to the efficiency of PV cell in that case? So as you know, efficiency of anything is output upon input. And you know that output of a PV cell is the product of its output voltage and current. So for an ideal input, for an ideal input on or ideal insulation falling on a PV cell, if we consider, then efficiency, the behavior of efficiency will depend on the product of voltage and current. So if you see, then we already know that voltage varies. The It has a positive temperature coefficient, and voltage has a negative temperature coefficient. So what temperature coefficient means is behavior of these parameters with respect to temperature. So for voltage, what happens is as temperature increases, voltage decreases. Similarly, for current, as temperature increases, current increases. And if you will look at the values of these respective parameters from any of the practically available solar PV cells, then you will observe that the the negative the decrease in voltage dominates over the increase in current, resulting in net decrease in efficiency of the cell. So we can in general say that as temperature increases, the efficiency of a PV cell decreases. In order to just think more about this, you can take a value of us from standard data sheets and calculate this. So let us move on to the next question. So in this next question, this is a numerical question where we are asked to consider a single solar cell where an insulation of 800 watt per meter square is falling on a solar cell, which is generating a voltage of zero point 0.5 volts and a current of 2 amperes. And we are asked to calculate the efficiency of the solar cell. Oh, sorry, we are given the efficiency of the solar cell and we are asked to find the area of the cell. Okay, so as all of us know that efficiency is output upon input, and for a solar cell, output is the product of the voltage and current that we are getting at the output, and input for a solar cell is the insulation that is falling on the solar cell, which is given in watt per meter square. When this quantity is multiplied by the area of the solar cell, that gives us the complete input to the solar cell. So if you look at this equation and substitute the values that are given, efficiency for our case is 12.5%, the output voltage is zero point 0.5 volts, output current is 2 amperes, and the insulation falling on the solar panel is 800 watt per meter square. So 800 watt per meter square, and here the value to be substituted was area of the cell. So based on that equation, and this will be in percentage, so we'll multiply it by 100. So if you'll solve this, the area of the solar cell will come out to be 800 into 12.5 by 0.5 into 2 by 100. So this will come out to be 0.01 meter square. So this is how we could obtain the area of a solar cell. Okay, so that's it for assignment 0, 0 run. We'll meet you next time with assignment 1 solutions.